This is Dr. Ashwini Agarwal, and in this video, we'll be talking about wide bandgap semiconductors and their manufacturing. This is a series of webinars that we have conducted covering semiconductor manufacturing processes, the assembly, testing, and marking and packaging of semiconductor dies. And in future, we'll also cover analog MEMS manufacturing and display fabs and their propositions. In this video, specifically, we're covering wide bandgap semiconductors, their value proposition, their markets and their inflection, their technologies and their technology roadmaps. Uh, we are covering the semiconductor manufacturing uh, processes and the semiconductor manufacturing tools. So it's a very good primer for this particular technology. And let us take a deep dive in it now. You're aware that we started this session sometime in October, and we have been doing these semiconductor primers so that the nation and the industry understands the concepts, the practices, the challenges, and the opportunity in these areas. These sessions are designed as primers. So we introduce the concepts and we introduce the manufacturing practice, and we talk to you about the trends and technology landscapes wherever possible. As of now, we have covered some of the modules here. Semiconductor industry primer was an extensive one, followed by the advanced packaging sector and what it meant, where the money is, where the growth is, how the overall sectors play out was covered in that. Today, we had actually originally planned to do MEMS and wide band gap primers, but we are fortunate to get some excellent speakers from the global industry for talking on the silicon carbide fab, which they were seriously looking at. And so what we have done is we are going to focus this session exclusively on wide band gap semiconductors and take a session on MEMS and analog computing separately with another global leader to cover the that as a separate topic. And then maybe at a point of time, we may even do a display fab to give you an idea of what that all involves. Let me actually quickly share the DNA of Applied Materials. We are the world's largest semiconductor and display equipment company. We don't make materials, we make the tools that make the materials. We are a $17 billion corporation, have over 24,000 employees in close to about a score of countries. And we are a heavy patent rich corporation, very IP intense corporation. And we are very strongly based out of India. So what you're seeing in the lower left side is our campus in Bangalore in India, where we have 5,000 employees. What do? We make the equipment that makes the components that are changing the world. So there is not a single chip in the world that would not have been touched by an applied tool in its production cycle. What we call tools are plant and equipment. Take a look at one of our tools that's there in this photograph at the lower side of the slide, and take a look at the men who are sitting on the lower corner. You will understand what I'm talking of. It's actually, so big that you can move trucks inside this equipment, and you are actually processing, miles and miles of semiconductor material and flat panel glasses to, layering them, creating circuitry depositions at an industrial pace. That is what applied material does. It makes the tools that make the uh, chips, display, and a lot of nanotech components today you see in the world. We are really having a very strong presence in the nanotech world beyond semiconductors and display. So, like in semiconductor chips, they say there's not a single display in the world which would not have been touched by applied tool in its production cycle. Each and every display maker, each and every chip maker is our customer. And then we touch so many other sectors, which includes solar, which includes flexible electronics, energy efficient glass. When Chennai is a customer, their energy efficient glass is not a film pasted on a glass; it's a nano coating done with our web tools. And then the applications are so many more. The currency note you're handling could have color changing threads printed by some customer of ours somewhere for that secure application. And we're working in life sciences and industrial coatings, so many areas. Uh, 5,000 people in India. Our global engineering center is here. We are very strongly ingrained with the academic ecosystem in the country. We have invested over 80 crores we have given as grants to Indian academia over the last decade of our association with the Indian academia in the country. Uh, we have multiple labs in the country. And as you can see in the slide, we are actually, IIT Bombay's largest industry partner. So the key message here is our innovations are making possible the technology shaping this future. And as you would have guessed from the core of the presentation so far, in the place we are, we carry a lot of IP for the industry as well. So the tool maker also carries a lot of IP in the industry. So as some people say, when you see Intel inside, Applied Material is a company inside Intel. And that's actually capturing the sum of it. So let me actually get on into the wide band gap semiconductor overview. And really speaking, you are all aware that semiconductor device landscape has been exploding over the decades. There have been waves of growth, and we are seeing no stoppage to those waves coming in. From the original mainframe computing of the 60s, we have seen the evolution of the desktop revolution in the 80s. We have seen the mobile revolution come in the turn of the century. And right now, we are seeing the Internet of Things totally exploding the market out, creating newer set of applications. So this is creating a tremendous inflection. The inflection is coming not just in the typical silicon devices, but today the industry is exploring even other materials and other compounds from the periodic table. And it is a discovered opportunity in the wide band semiconductors for specific type of applications. And that is in power and RF applications. Some of these wide band semiconductors have very interesting properties, which the conventional silicon is not able to match, and it's creating opportunity. So if you take a look at this chart itself, you're getting a feel of what we are talking of, and you can see that there's something called a band gap energy, and compared to silicon, silicon carbide and gallium nitride are giving a phenomenally higher band gap energy. So the question is, what is this band gap energy? It is the energy required to excite an electron from that valence band to the conduction band. So if you have done physics, you will remember that you have typically a planetary system of a core which is made of neutrons and protons, and you have electrons revolving as many planets around this core, and they are positioned at discrete orbital positions which are linked to the specific energy state relating to that particular compound. And then as you look at the the further and further most disposed orbit, you come to the outermost orbit, which is called the valence band. And if the electrons in this are given enough energy, they can exit to come into a free flow, or what is called the conduction band. So really speaking, if the band gap is large, then a higher critical electric field is required to initiate the ionization, to create that free flow of electrons. And one of the simplest things that one can keep in mind at this stage is that for a given breakdown voltage of a device, the wide band gap semiconductor will be smaller. So let's actually take a look at this a little more with a little more interest. And you can see it in this particular slide. If you take a look at the right-hand side diagram, what it is sharing is that there are certain intrinsic properties of the wide band gap semiconductors, which is faster switching speeds. Okay, because it will switch faster, it will have a higher switching frequency. Therefore, your passives relating to that particular semiconductor device, the capacitors or the inductors, they will be smaller. Now, why will they be smaller? Why is there an inverse relationship between the size of the capacitor or the size of the inductor and the switching frequency? That's because these are energy storage devices, and the energy that they store and they pass on are linked, among other things, to the capacitance and the switching frequency. So if the switching frequency increases to get the same energy transmission or storage, your size of the capacitor or inductor will come down. So in a typical, charger circuitry, for example, the moment you use a gallium nitride device, power device, your size of the charger will reduce dramatically. Okay. Moreover, there are other advantages. It's the thermal conductivity of some of these materials is higher, and therefore the cooling needs come down. And these all, impact the system functioning and the system size and weight dramatically. So if you actually take a look at it, even though there are other parameters which indicate that, the temperature could be higher or whatever, but the fact remains the actual temperature comes down dramatically in real life operational conditions. And therefore, it is, for a lot of power applications, wide band gap devices can be very, very advantageous in the final system design. So this is what is actually being acknowledged now, that the wide band gap semiconductors are dramatically impacting power electronics, among others. They are impacting RF also, they're impacting quite a few other areas. But the fact still remains that the wide band gap semiconductors are impacting power electronics with a significant revenue impact. Okay, still a fraction of the total market, but it's actually growing. Applications are exploding out. It's going in conventional power areas, and then there are newer power areas coming in. So you can see that in this slide, where at the top end you can see these are the conventional established power applications which are still growing. That is solar and wind and motor drives and UPSs, or at the higher end the rail traction applications. These are all growing. These are all current markets which are growing. But there are new market applications which have started coming in, which are electric vehicles, and you have your charging infrastructures and energy storage devices, and all the power electronics relating to it. That's actually slowly evolving as the niche area for our wide band gap semiconductor devices. So what is the manufacturing chain? I have covered a part of it actually before, but as a snapshot, just sharing what is here is that you start with an ingot, you slice it off using an appropriate exfoliation process, which could be laser or wire saw, and you lap and polish it out to create that wafer. And then in our wide band gap manufacturing, you will do on that base substrate, which can be silicon or silicon carbide. You actually do an epitaxial coating. Okay, so you grow a thin layer of gallium nitride or a thin layer of some wide band gap semiconductor on it, and then you start processing it. Okay, which is the conventional device creation process of alternately creating a passivation layer and then creating your transistors on it, creating the vias, creating the connects, and ultimately creating that processed wafer with dyes on the wafer, which is then taken into a back-end process where these are all tested and they are all diced, and then they are picked and placed on appropriate packaging. The final package is created, and the device that is created is then going into a finished product, which is going into some application, and that is the value chain which is there, which is actually split in two parts. Conventionally, the front end where the wafer is processed, and the back end of the factory where the dies which are made in the front end are getting inspected, sorted, die mounted, encapsulated, final test, and final product comes out, which is what you see. So the heart of it is, of course, the die, which is actually, you see the processes here: the epitaxial growth, deposition, coating, cleaning, litho, etch, implant, anneal, polishing, wafer probing, and some of these processes are done, you know, several times. So in a typical device creation, for example, in CMOS, it can run to over 1,000 steps. So it's a pretty rigorous, process intense thing. And where do these devices go? You have, typically we talk of gallium nitride and silicon carbide as the two mainstream wideband gap semiconductors. And as you can see, the wideband gap, the silicon carbide plays at the higher end. Silicon carbide is playing at the higher end. 600 volt and above is where the silicon carbide devices find their reason to be. And then the gallium nitride is typically 40 volt plus to the 600, 650 volt. So there is an area where the two device technologies clash, but otherwise, to a great extent, their reason to exist is pretty much separate, and the markets are separate. And the markets are interestingly growing at a phenomenal pace. Take a look at the gallium nitride growth rate, which was projected for 14 to 20, 95%, and silicon carbide, which was at 22%. Now, these are very, very high growth rates. 22% growth rate is not small either. But of course, gallium nitride's been growing very rapidly because it is at the low end, and low end is where the consumer markets are, and they are now taking traction of this particular device technology. Even now, the share of the wideband gap semiconductors in the overall power devices segment is small. Okay, but it is very clear that it is going to grow rapidly over the years, and this is how it is foreseen over the next uh, few years. The power semiconductor market itself is $44 billion. And if you take this at 10% of this entire thing, you are talking of close to about $4 billion is now the projected demand for GaN and silicon carbide by 2024, 2025. So it's actually a market which is very, very interesting from the investor point of view. It is this market where devices were constrained that impacted the auto segment. Okay, but that has a separate story. The clear message here is there's a huge opportunity that is here, and it is not just that you can walk in and take it. You have to create this market as well. As you can see from it, the markets at low end are travel adapters and wireless chargers, and higher end can go in for something like rail traction devices, to telecom networks, to servers and data center applications. And you have a huge opportunity that is shaping up. And this is getting validated now. Okay, this is actually getting validated now. In 1920 is the time when the gallium nitride-based mobile chargers have taken off in a big way, and it's actually creating a pull where the gallium nitride is going creating volumes, and it's moving into the mainstream. Not quite where the silicon is, but clearly the inflections are visible. And this is the technology landscape that we see that could be there. One is that and conventional Moore's law type scaling down of the die, increasing of the transistor density on a particular footprint area, and then you have the evolution of newer process architectures, which can be the vertical gallium nitride or monolithic gallium nitride, or devices like driver gallium nitride, where you actually have multiple high energy mobility transistors integrated with a driver IC on the same chip. And these applications are not all that far away. We are talking not of a decade away. We are talking now. So we already have a reasonably stable, workable p-GaN architecture, which is there in the market now. and clearly the volumes are growing, so it's bringing conditions in which the equipment industry will be able to deliver improved yield and cost production lines. Monolithic lateral GAN is moving towards the reality. But what is more interesting is that even the subsequent architectures are not all too far away. They have been validated in labs. They are moving into smaller niche applications, and they should get into the mainstream over a period of time. So let us actually take a quick look at the manufacturing process and what is the applied portfolio. You must also realize that if it was so easy for, with all, if there were so many, functionalities to these wideband gap semiconductors, why did they not get replaced by silicon? And that is because of cost and manufacturing economies as a commercial reality. So the fact of the case is that it is not easy to make a coating, I mean, epitaxial coating of a gallium nitride or silicon carbide on silicon. It's actually quite a challenge because the lattice structures of the bare substrate and the epitaxial coating are radically different, and because the resulting stress that gets created, the crystal the wafer can get distorted, and it will have a lot of defects. And the defect density in a typical gallium nitride crystal can be as much as a billion per square unit of measure. And it was only in the last few years that this defect density has been controlled a lot better, so that this technology is now being seen as a potential mainstream technology. Even then, it's not reaching the there are constraints. So you don't actually make these wafers on a 3-inch wafer, on a 12-inch wafer. You don't make it on a 300 wafer. You find that because of the warpage that can happen because of the crystal mismatch and the production constraints, people are actually making gallium nitride and silicon carbide on wafer coupons of sizes 4-inch and 6-inch, and maybe even 8-inch. But nobody is really looking at a large scale 12-inch production. So this is an interesting thought that I want to leave you. You're not working with the most costly equipment. What I'm doing, typically when you create the device, you're going to lay it on a base substrate. And typically, the choice of substrate has been sapphire or aluminum oxide. And when you have GaN on aluminum oxide, you're actually looking at working on using it for a LED application. Or if you are looking at silicon carbide, that's great because there's a very close lattice matching between a silicon carbide GaN crystal. And then the only thing is that it's got its own cost implications and manufacturing process implications. So people have looked at silicon as a base substrate because it brings the CMOS cost advantages into the play, the silicon manufacturing cost advantages into the play. But then there are certain manufacturing challenges of its own type. Irrespective of these, the fact remains that typically creating that crystal, creating that device involves actually starting with a base crystal with an epitaxial coating on it, on which you will typically create your AlGaN and PGaN layers. And the idea is to create electron cloud in a particular layer, and then create your wires in such a way that you can actually uh, you know take the advantage of that particular electron cloud. And again, there's a particular video which I wanted to share, but it was not coming too clearly. I'll send you the link and do enjoy it and understand the basics from there. But if you take a look at the manufacturing process itself, this slide actually gives you a view of what we have from applied material, which is when you take a look at the complete uh, equipment portfolio here, other than that of creating the epitaxial layer, the entire process, the tooling that is required, whether it is creating the implants or the iron etch or the PVD, CVD coating, the metrology, the plating, the CMP, which is the planarizing tools. We have the best in class equipment out there. I have a huge deck on it, but I'll not get into it. But the key message I want to leave you is that this is not just our tooling for the CMOS which has been brought here. These are not just our old generation 200 tools being put here. As a company, we realize that there's a huge inflection that is taking place in the with the evolution of IoT and the revolution in communications and the auto sector and power and sensor markets. And therefore, we created this division called Icaps, and it's taking the words from the each of these sectors to define it. And it's actually a recognition of the mega trends and device technologies that are shaping here. And we have literally built our tools for these product portfolios ground up. So even if they are our earlier generation tools which are used in 200 era, the new tools that are there, they're not refurbished tools. They are all repurposed because the sort of plating that you need to do for these particular applications are radically different from the CMOS level processes that you wanted to do earlier. And therefore, there's a lot of customization that has happened on these, which actually builds a huge opportunity. And which is why we keep on emphasizing that be very careful when you start looking at your tool planning in these areas, because people think they can take some of our earlier generation tools and actually look at just working with them. But then there will be other disadvantages and other constraints that can come until unless you're using a tool which has been properly configured, which has the right repurposing, so as to speak, so that it can deliver the best known methods and best results in this marketplace. So the key message is this is not a 12-inch wafer size processing tool. Okay, this is not in this industry, this particular niche. The mainstream manufacturing is not a 12-inch wafer, and therefore the tools we have are specially configured to handle even lower templates. Okay, and they can handle multiple sizes, and they are tuned for giving you those results. And that's the key message we want to deliver at this point of time. Uh, I guess this is the core that I want to deliver in the time frame that we have. We'll take a specific question on this separately.
Good afternoon. My name is Sunil Kaul. I'm a senior advisor to Visicon Power. I'm based in the US, and it's a pleasure to be invited to this forum today. And unfortunately, because of COVID, we were unable to travel to India, which we were hoping to do. But hopefully, in the next several weeks, we intend to be there in India. Um, I thought I'll start out by just trying to explain how Visicon fits into the overall portfolio of companies. Visicon, which was based out of Halol near Baroda, the focus is silicon carbide. However, the genesis of how Visicon came about is in 1994, the promoter, Harshad Mehta, he acquired the GE Semiconductor Group out of Pennsylvania. And then over the subsequent years, he did a few more acquisitions of Harris and Microchip and all that, that you'll hear a little about, where we're doing silicon carbide foundry work. Sicamore Semi, which is on the right side, as you can see here, is a pure foundry play. It's a company that's based in a town called Bend up in Oregon, and their focus is silicon carbide. And we're also developing some gallium nitride stuff that Michelle will talk a little about some of the work that we're doing in the area. Now, this is a pure foundry play, and the connection between Sycamore and Visicon is the technology that is being developed in Sycamore will be transferred to Visicon, which we'll be setting up. In Halol, we have a company that's been around for 50 plus years called Ratan Shah. It's a publicly traded company, and they serve a lot of the well-known Indian customers and even abroad. But in India, you have Mahindra, you have Tata. They also focus on some of the specialties in the area of HAL and even companies like entities like the Navy. Um, Going on to the next slide, I think most of you are familiar with the overall power electronics market. And this is obviously a market that we believe is very relevant for the Indian conditions. And also, I think we are looking at even doing some exports out of India, which I'll explain in just a bit here. Many applications we believe where silicon plays eventually over time, silicon carbide and then gallium nitride will play. Again, a lot of you are experts in this area and understand it, but we believe that some of the initial entry that we will do it will be through Visicon for silicon carbide. Then over time, we expect to get into the gallium nitride applications. I think again, hybrids and electrics and renewables and switching power supplies, these are applications where you have gallium nitride. And we're already in discussions with some large OEMs in India about identifying some immediate application for silicon carbide. And hopefully, as time goes by, we will collaborate with them. And we're actually very excited by that opportunity to do that. I think silicon carbide offers many advantages as we collectively know. But one of the areas that we're focusing on is to set up a semiconductor fab focused around silicon carbide, which is obviously power electronics. Our belief is that while there's obviously much larger opportunities for analog type chips, but the investments required are there in the billions of dollars, and the return on investment obviously would be much longer, and also the associated technology risk, because you're looking at leading edge processes at 16, 14, 7, and even down to 3 nanometers now. In contrast, power electronics, you're dealing in micron type lithographies. And because of that, the investment costs, as we've shown here, we believe will be significantly less in the 300-400 crore type investments. And we believe that that's probably the right way to at least start. And our belief is that through a company like Visicon, that we can demonstrate why a silicon foundry is possible in India. And hence Visicon, we're very excited to be able to demonstrate that. Plus the fact that we can demonstrate that it can be made in India within the infrastructure and the talent that we believe is widely available there. Our belief is in philosophies around identifying what we call the must, is identifying technology that we believe are commercially viable and technically viable in the markets. So find a technology, make sure that it's manufacturable, ensure that it's usable, and then obviously, there's customers that would be willing to buy it and we can sell it. So what we're trying to do is, in the same case here in Visicon, is to look at companies and markets that we believe are very relevant for silicon carbide initially, and then over time we evolve into the gallium nitride type applications. So what's our strategy? It's very simple. At one level, we're a deep believer in collaboration, and we have very excited by and very pleased by the support of the government of India. And we are in discussions with them about hopefully signing an EOI for the gallium nitride that, again, Michelle will talk about some of the work we're doing in that area. But also there's a very important role that the academia and the public sectors play, the PSUs. We have already hired somebody from TIFR in Mumbai. He's actually one of our first employees. He's a PhD from there, and we're very happy to have him on board. But we're also in collaboration with IIT Delhi, IIT Chennai, Bombay, and then premier institutes like the Indian Institute of Science. And while we're doing collaboration, because we believe there's talent and some brilliant minds there, in parallel, we're setting up Visicon that will be a fully integrated manufacturing entity, right from wafers to semiconductor packaging, and then eventually into power modules. And again, these would be high voltage, high power module applications. And this will be the first of its kind where you're providing a fully integrated entity in India, and we're very excited. And the first phase is establishing an epitaxial manufacturing service. That should be up and running by this summer. The second phase will be setting up a semiconductor packaging line for power electronics. And the third will be the actual chip manufacturing, the device manufacturing. So we have a business plan around that. And I think over the next 2 to 3 years, we're excited to be able to see how that progresses. At this point, what I'm going to do is I'm going to hand it off to my colleague, Michel Francois, and he'll talk about some of the deployments that we've had, and then talk a little more about some of the gallium nitride work that we're doing. And again, thank you very much. And I look forward to meeting hopefully some of you on one of my next trips to India. Take care.
Good morning, everyone.
Are you
Thank you
hearing
for
this?
inviting
Yes, sir.
us to this conference. As Sunil mentioned earlier, I will be presenting the second part of this presentation. My name is Michel Francois, and I am the Director of Device Technology Development at Sycamore. There are two key players in this program. Both are well-established companies in the United States. The first one is Silicon Power, located in Malvern, Pennsylvania, and the other is Sicamore Semi, located in Bend, Oregon. Silicon Power, the company located in Malvern, Pennsylvania, is involved in developing critical semiconductor components for several military application, military smart weapons. As you can see on the top left-hand side of this slide, the different weapons the devices are used in. And just to name a few, we have, let's say, the Patriot, the small diameter bomb 2, the small diameter bomb 1, and a few more, and few others. Now, Silicon Power, we have also developed high power silicon and silicon carbide devices for pulse discharge applications. We're talking about SGTOs in the range of 3 to 5 kV and bigger devices that can go up to 15 to 20 kV. These devices cannot be wire bonded, so we have developed and still hold the patent on the thin pack packaging for module technology. By thin pack, we mean it's like basically attaching a very thick ceramic leads with big metal lines on top of the device. So that will allow you to conduct very high current. So these ThinkPack devices are used to, for example, build our power semiconductor half bridge power modules, N-type semiconductor discharge switch modules. And then we go to the vertically integrated semiconductor. That's for very big systems. Using, for example, the press pack power devices that are actually being built in India now, and also the high power GTOs, we can build power modules, big power systems, power electric building blocks, and many more, even very high, big power systems. On the bottom left side of the slide here, you could see the Silicon Power's portfolio cover a really wide range of using many applications. And these devices are used, for example, here for as pulse power e-gun, all the way down to electric vehicle. We're talking about rail guns, um, microgrids, and data centers. The second key player is Sycamore Semi, located in Bend, Oregon. Not only Sycamore is participating in the high power WBG wide band gap markets such as industrial, electric utilities, electric vehicles, electric transport, renewable energy, communication, aerospace, military, and defense. Sycamore is also working with small groups such as universities by running smaller labs for developing new devices. Remember this, small labs are often where the disruptive advancements are made. So we are working in developing new devices with many different universities in the US. We will do the same in India. Actually, we are working with a university in India, IIT, on developing processes. This company started in 2019. We have put together our technology roadmap here, and we have been on track. Our first year, we have developed silicon carbide diode and MOSFETs. We're talking about in the range of 600 volts to 1.7 kV. In 2020, um, we did team up with the University of North Carolina State, and we have developed with them a 3.3 kV JBS FET. JBS FET is a combination of JBS diode and the FET MOSFET on the same chip. We have also developed silicon SGTOs and S diodes ranging from 3 kV to 7 kV, and a 6-inch silicon line also for SGTO from 3 kV to 7 kV. As you can see here, we check mark these. That means they were done, were completed. So that's why I mentioned before we are on track. This year, we plan to develop higher voltage silicon carbide STTOs and IGBTs, more power devices, and also the smart power devices. And we are very focusing on GaN processes. We'll go over that a little bit later to see what we are doing in there. And the following 2 years, these 2 guys, we plan to develop even higher power silicon carbide and gallium nitride devices. And also, we want to get involved in silicon photonic processes. On this slide, we want to show great accomplishment, the 3.3 kV silicon carbide JBS FET that we have completed with North Carolina State University. Gotta say that there are only 2 fabs in the United States that are capable of fabricating this JBS FET from NCSU. The other fab did one before a 1.2 kV JBS FET process, but we are the first to run the 3.3 kV JBS FET. We are the only fabless company that has run the 3.3 kV JBS FET. We have completed also early this year a 15 kV silicon carbide MOSFET for a different fabless company. And as you can see underneath here, that 3.3 kV silicon carbide JBS FET, you can see the target applications. It's hybrid electric vehicles, renewable energy, cover the whole 9 yard, mobile charger adapter, industrial motor drives, rail traction, UPS, data center, electric power grid, military, aerospace, heavy vehicles. So this is going to have a very wide application, and most people are under 1.2 kV. So we completed our 3.3 kV silicon carbide JBS FET. But our main goal this year is really focused on the development of gallium nitride process. This graph shows three areas, for example, where the gallium nitride is going to really zoom up in terms of money. You can see in 2027 and 2027, it's a very big market. But as a small company, we cannot compete with the big guys on, for example, the gallium nitride radio frequency devices, and also on the power semiconductor devices. So our niche is we want to focus on the opto semiconductors. And not only that is not crowded yet, but we think we have one of the best, or maybe the best technology in this area. So it will be a market that will be very favorable to us. Our first device we would like to build is the solar blind UV photodetector. And this is the rationale behind this. We all know that the sun is the primary UV source. Approximately 9% of the sun's radiation is UV. So UV detection, we know also, is very important from different application perspective, especially in space, flame detection, and everything. So consequently, due to the nature of the working environment, these devices are exposed to significantly harsh environments. So because of that, so conventional silicon-based devices are inefficient in this regard. So this is where these WBGs, wide band gap devices, come really very strong. So gallium nitride and aluminum gallium nitride, slide gallium nitride, and also silicon carbide and zinc oxide, wide band back, they really fit in that area. So these devices remain blind to visible and IR irradiation, while at the same time allowing to detect UV without significant modification. So they also possess higher thermal conductivity than silicon, which enables their efficient functioning in high temperature and also harsh environment. So for UV detector, UV photodetector, so it's very good because it will block. It can be used in very harsh environments. So we call this a photodetector solar blind UV detector. Then niche application areas, our market segment, are these four different areas. I've mentioned about space and environmental monitoring. These solar blind photodetectors are very important. With the gallium nitride photodetector, we can also get involved in biological and chemical analysis. So aluminum gallium nitride photodetectors, to the simulation of the biological effects of the UV light, for example. We can study that on the skin, on the eyes. So we can use these photodetectors for that. And flame detection, very, very important. It's basically environmental. We're working on the environment here. And the reason they mention flame detection because the growth of this market can be attributed to the increasing human and property loss due to fire breakout. So here in Bend, Oregon, for example, last year we were basically shut down for more than a month because of fire. The factory, not in the factory, but in the in the mountains, because it's a dry area, so a lot of fires. So if we can prevent these, when they start from the beginning with gallium nitride photodetectors, that would be great. And other area that this talking about our niche application market is in the remote control technologies. So these are the four areas we are focusing um, for, and we are developing this gallium nitride photodetectors uh, to be used in these areas. Then teaming up with Drexel University in Philadelphia, we have developed a photodetector on gallium arsenide previously using a new structure. And I show a picture of that new structure. And that same new structure that we have developed, we're going to apply it to our gallium nitride photodetector. And that is by using a device layer structure with two reservoirs of two-dimensional electron and hole gases separated by a region that absorbs light. And on top here on the bottom, there are two connections, Schottky contacts for the anode, cathode, and anode. This is a carrier concentration of energy level. You can see here where we hold the electrons, and here where we hold the holes. And under a bias voltage of only 0.5 volts, you can see all the electrons move up here and the holes down here. So we're basically creating a sea of electrons that can be pulled out very quickly. So we're going to apply that same technology to gallium nitride. And our key value proposition here is developing an aluminum gallium nitride based optoelectronics devices with higher sensitivity by using this technique, speed, you have a sea of electron waiting, lower power usage, and capable of operation in high temperature and harsh environment. Again, to summarize, our value proposition is to develop a aluminum gallium nitride based photodetector of high bandwidth and efficiency while consuming lower power, capable of operation at high temperature under harsh conditions, and at the same time being economically viable and environmentally sustainable. So again, it's repeated here. And the key partners are Nanoglass Photonics, which is a fabless company, the design group. And then with our Sicamore Semi in Bend, Oregon. And if we look at customer segment, the industry, it's chemical sensing, as you mentioned before, space applications, remote control technologies, and fire detection that we have previously shown you the slide on these four areas. And the combination again of academia, universities, and national labs. And other area we would like to get involved also is the silicon photonics. The object here on this slide of this project is to develop a digital receiver using efficient all optical analog to digital converters, an efficient electro-optics polymer, a base optical waveguide that is integrated with photonic crystal. We're going to put photonic crystal, PHC, which is photonic crystal structures, forms a leaky waveguide that redirects light to form a spatial light modulator, SLM. So that will be done on silicon. We have all the electrodes, everything like normal processing silicon. And at the end, we will make this optical waveguide. And on top of the optical waveguide, we have that 1D PHC layer. What I mean by PHC layer is photonic crystal layer. So that really a bunch of we basically cut, and that is like 49 nanometer openings in this waveguide here throughout, and the light would come here and this and just the wiki waves. But this is more in actually we did the simulation already. We have everything ready, and but this is next year we're gonna get involved in this optical waveguide for. And I would like to thank everyone for listening to us. I hope it wasn't that painful, and thank you again for inviting us.
So if there's anything else, then you please, otherwise, you can conclude with whatever comments you would like.
I really appreciate your patience with the session, third in the series. Irrespective of the few internet glitches, we have had a pretty nice session. All the content will be made available on the internet over the weekend, and look forward to connecting and taking this discussion ahead. Cheers. Next time, maybe the analog fab.
Ashwini, I'll just drop in for a minute to say to thank you very much and your team. I was very curious to learn, and I thought it was for somebody like me who's non-technical, who doesn't know much, you still managed to bring it to a level that somebody like me could claim to understand a little bit of what you were talking about. But your team was super, and also the way you took us through, and I think it's a fantastic thing that is happening in a series. For some of us, pure awareness, but I think that helps. The industry gets encouraged by what is happening. So thank you very much, both Raju for organizing it and Ashwini for putting it together for all of us. Thank you so much.
Thank you, Vinod. Really appreciate it.
Thank you a lot, Ashwini. Thanks, Ashwini. Thanks.
Goodbye till.